recording. And I'm going to switch to the document camera. Okay, we'll get there. So, okay, Monday will be a test. All right. That also means I would like for, okay, hang on, I'm gonna do this. I want everybody to think of a number between 1 and 20. Oh, don't tell me yet. Think of a number between 1 and 20. Okay. All right. What was your number? 17?
3.
16, 15, 12, 11.
7.
What? Did you say 13?
13.
Okay, you get to do problem number 4 on the document camera on Friday.
Okay.
And these are review problems, the review problems in the chapter. So it's review problem 2-4.
Okay.
Yeah, review problem 2-4. And it should be the same problem that's in the homework for the chapter review. And did you say 3 or 7?
I said 7, yeah.
Yep, you get problem number 6. And Kayla, she doesn't know it yet, she's gonna give us a written one up on problem number 5. So yeah, so we'll be able to share her written solution for problem number 5. But for presentation in class, you get 13. You get 7. And by the end of the semester, people will have done 2 or 3 different presentations. So it's going to roll around. Everybody's going to get lucky. You guys just get lucky early. You guys get lucky early. So you're going to present those. Okay.
Is that something that we can just like work beforehand?
Oh, yeah. And you actually, yeah, you bring your paper. Because I don't just work them cold. Yeah, I don't work them cold. And like I said, those 2 are actually in the homework. So, yeah, they're in the homework. All right, so I'm going to do a problem. So just giving you guys a heads up. So Kyle and Elena, because of the way this class is usually done, usually we require calculus for this class. But because OSU is now using it from a variety of different things, that general physics one, you don't necessarily have calculus in here, so I have to do both sides of it. And you guys will pick it up, the calculus that we use, you'll pick it up really, really quickly. It's not until you get dynamics, like most other things, that things get really, really complicated and are in there. The other part where we end up using calculus and statics a lot is when we start doing centers. Where's the center of gravity? Where's the center of the different things? And if you're trying to figure that out on a shape, turns out you're going to get it in Calc 2 is where you actually get it. But the reason we can do it from an algebra-based class is there are tables of them. Okay, there's just sheer number of tables of them. So from that perspective, that's why we're going to do it. But I'm going to show you a calculus technique so that everybody has it and you've all seen it. And if you run across a problem with it, for those of you who haven't had calculus in this part, just holler at somebody and we can show you how to do it. That part's pretty straightforward. So I got it on the document cam. So we're going to start with a bracket. And this bracket looks like this. So it's an eyelet bracket. And we've got a force that's being pulled this way, and it's a 5 kilonewton force. We got a force that's being pulled this way, and it's a 4 kilonewton force. And then we have a force that we're going to have to apply here, and this is our unknown force. And we're told that this is a 30-degree angle, so my picture is not necessarily drawn to scale. And the question is, we want to know that with what the magnitude of this force is, such that the resultant force is as small as possible. So we want to add up these 3 forces so that this resultant force is as small as possible on that bracket. So what that means for those that haven't sat there in calculus, and you guys are probably getting it in differential equations right now, what that means is that that first derivative, I think it's with respect to f, yeah, that first derivative with respect to f has to equal zero, is equal to 0. So when I do that derivative, I either to get a maximum or a minimum, I'm setting that derivative equal to 0. But the question is, how do we get there, right? That's really how we get, the question is how we get there. So the first step is to find the resultant force. And what we know is that the sum of the forces in the x direction and the sum of the forces in the y direction all have to equal 0. So if I do that, the sum of the forces in the x direction is my 5 minus f, and that's sine of 30 degrees. And this one is going to be f cosine 30 degrees minus 4. So that gives us that the resultant vector, the magnitude of the resultant vector is going to be the square root of 5 minus f sine 30 degrees, plus, and that's squared. And then I get f cosine 30 degrees minus 4 squared. Where did I get what? That's from right here. This is that's this force in the x direction. That's subtracting this force in the x direction.
Yeah, it just looked like a 3.
Oh, no, it's 5. 5, sorry. 5, 5, 5. My markers are a little big, but it makes it easier for the document camera, Okay, so now you get to do the Gorey algebra. I will spare you that right now, because I'm pretty sure you guys can do all the Gorey algebra. So I'm going to square everything, and I get f squared, and I'm going to get f squared minus 11.93f plus 41. That's going ahead and squaring it under here, rearranging it so we get all the terms together, and I get this part. All right, now remember, the big thing is when I do that derivative with respect to r, that one right there, that's got to equal 0. So if I do the derivative there, so those of you who have seen this and have done it in calculus, what this is going to be 2fr dfr df, and this is going to equal 2f minus 1193. Because when I do a derivative of a constant, it's 0. And basically for you guys, what this says is if I have something f to the n power, what's going to happen is n minus 1. And when I get something to the f0, that's equal to 1. The other really good news is you can look that stuff up. There's lots of tables and you can look that stuff up. Okay, so we get this, so once we get to this, we're going to set this to 0, and this just becomes 2f minus 1193 equals 0. We solve for f, and f gives me 5.96 kilonewtons. Now that here is the magnitude of this right there. But then we want to figure out what the value of FR is. Well, that's easy. Once we have that value, we plug it back into this equation, and FR is 2.33 kilonewtons. So given these two forces, to give myself a force here, the smallest resulting force that I'm going to be able to see on this bracket is 2.33 kilonewtons.
Sounds like somebody will.
And you can do the same thing for the maximum. You know, it's when that derivative is equal to 0. It's either going to be a minimum or a maximum. And in this case, it's a minimum. Does that make sense to everybody?
For the FR, the algebra, did you just FOIL that after you squared?
What?
After you squared the square root and you solved it algebraically, where it says FR equals square root of 5.
That's squared.
Whenever you solve for it, do you FOIL that or?
Well, you're asking if you FOIL it. What you got to do, here's the Gorey algebra. I got to do 5 minus f cosine, oh, that's f sine, sorry. I got to do f sine theta, f sine of 30 degrees, times 5 f sine 30 degrees. I'm going to FOIL that, and I'm going to FOIL the other one. Right? So I'm going to end up with 25 minus 2f sine 30, right? Or no, I end up with, should be 5. I end up with 5 on that one. And I end up with another 5 on the other one, right? And then I get f squared sine squared 30, right? And I'll do the same thing here, and ultimately it will simplify to f squared minus 11.93f plus 41. And that would be under the square root, which is why I have to do the FR squared. Yeah. Lots of pages of Gorey algebra.
I was just wondering about if you FOIL it and how you.
Yeah, you got to do it underneath the radical, and then you square it to get rid of it. Okay, we're good? All right. So, where we're headed and what we're doing in this last section is getting position vectors. We've already kind of started talking about them, and we started talking about what a unit vector is. So, I'm going to show you this problem here. So we've got a vector. This is a 500 Newton force, and it's directed as shown. Okay, 500 Newton force is directed as shown. And then we say, what nearly is the component vector representation? Because one of the things that we're going to have to do is get that position vector. Now, what's going to happen if I'm doing this is actually a Fundamentals of Engineering exam question. This would be a question that you would see on the Fundamentals of Engineering exam. And we're going to kind of talk through it. So the big thing is, one of the easiest ways to do it is figure out which one of these has a magnitude of 500. That's quick and dirty, because this is going to be a 500 Newton force. Now, which one of these has got a magnitude of 500? Then you got to make sure your positive and negatives are all right. So text taking skills 101. So I can do it, but for what I want to do right now, I just want to look at the position vector. What's the vector that goes along that piece? And how do I get that position vector? Remember, we said that one of the things that when in doubt, you're trying to work on a problem, when in doubt, you want to figure out what the unit vector is. Okay, you want to figure out what that unit vector is. So how do I do that, right? How do I do that? Well, let's look at this picture, because this picture is going to help us out to figure this out. So if I'm looking at this, and I'm looking where the tip of this arrow is, it's gonna end up being answer D. That's gonna give me how I'm going to find this position arrow. Now, that one is probably not going to be, which one of these is the directed force. Turns out the answer, if you want to work it through, is answer B. Okay? You want to work through answer B, but the reason I'm starting with this is an easy one to look at how you're going to calculate a unit vector. So here's what we do. So first of all, let's draw the position vector that's given to us. This vector F. Well, that vector F is along the line that is 3 in the y direction, it's 7 in the x direction, and it's 8 in the z direction, all positive. So I can write 7i plus 3j plus 8k. Now, that's not the force vector, because the force vector has a magnitude of 500. And that certainly doesn't have a magnitude of 500. But it does give me that unit vector, so I really want to write FU unit vector A, and that becomes, now this becomes, that's not a vector, this is a vector. It's going to be 500 times whatever my lovely little unit vector looks like. And that's actually what we're solving for. So this isn't that, but this, I can take this with a magnitude of my unit to get my unit vector. So now, if I know that I'm at a 7 and a 3 and an 8, let's calculate the magnitude. Magnitude is going to be 7 squared plus 3 squared plus 8 squared, square root of all that. So I'm going to calculate that, so I get 7 squared plus 3/8 squared plus 3 squared. That ends up being the square root of 122, if I've done that right. Which is going to give me nominally something that's 11.0. So to get my U of A, I've got to take 7 divided by 11. I've got to take 3 divided by 11, and that's in the j direction. And I got to take 8 divided by 11 in the k direction. So that's going to give me my unit vector is going to have 0.636 in the I direction. It's going to have 0.273 in the j direction, plus 727 in the k direction. So now if F U of A, that's 500, this is going to be 363 in the K. This is 137, it's actually 136.5 in the J. And it's 318 in the I. So I've got the magnitude of the vector times my lovely little unit vector. And if I put the 500, and that's why it says what's nearly, because that one, depending on how you round, could be 363 or 362. It can be whether or not I'm carrying 11.0 or I'm carrying 11.04.
So you just multiplied those by the 500 to get the...
So I could find any vector of any magnitude that follows or acts along this line because I found the unit vector given by the dimensions that they gave me in the picture. Yeah, and so this whole last section of, right before we get to the review, is looking at dealing with these kinds of how do I build my unit vectors? And what do my unit vectors look like? And how do I get there? So let's look at a couple of them. And that's what we're going to be doing. We're going to be looking at several of different of these as we go through to get practice at them. And it's how do you read these pictures? I mean, for a lot of you, it's how do you read the little picture, right? So here's a problem. I got a sign. So there's my sign. So that's why it's going to give you a variety of these little pieces. So from point A on the X side, it's 5 meters away from the Y. It's 2 meters to this point D, it's 3 meters to this point A. This pin is 2 meters away from the Z axis, and it's 3 meters away from the B axis. This pin is 2 meters in this direction, 3 meters in that direction. So we're going to look at F of C. Okay, we're going to look at F of C. So I'm going to look at this vector. And look at the direction of this vector. So I've got that direction of that vector. I'm going to try and keep it all on one piece of paper here. It's going to be a little tougher. So one way you can do this, you're going to say, all right, I'm going to find R. This is a vector that lies along this direction. So we're going to do R. I'm going to do my initial point here, which is 0. And I've got a -5 here to get that second one, partially because my vector is going in the wrong direction. Okay? My final position is 0, my initial position is 5, so I'm going in that direction, so I'm going to do that, and that's along the I direction. Since we're doing C, okay, my final position is at -2, and my initial position is at 0. And then my Z, my final position is at +3, my initial position was at 0. So I can use that technique to help me and keep it straight. So this becomes -5I -2J plus 3K. So that's a vector that lies along this line. So now I can find the unit vector. Okay, now I can find the unit vector. So the unit vector, I got to find the magnitude of R. The magnitude of R is going to be the square root of 5 squared plus 2 squared plus 3 squared. So it's going to be 25 plus 4 plus 9. We'll go ahead and do it in my calculator. It's 38. Square root of 38. And then you can do the square root of that. And that square root of that is 6.16. So the unit vector along R is going to be -5 divided by 6.16. -2 divided by 6.16. Plus 3 divided by 6.16. This is 0.812. That's in the I direction. 0.325 in the J direction. I get 0.8 or 487 in the K direction. So now I've got my unit vector. So that's the unit vector that lies along here. So now I can write f of c with all its gory directions, right? Because f of c, or fc, is going to equal, so vector fc equals f unit vector r, because that's what we figured out, and this is r along the c direction. And that's where my vector is, right? That's where my vector is. So I'm going to do, it's 400, so I'm going to do 400 gives me minus 325 in the I direction. Gives me minus 130 in the J direction. .487 times 400. It's going to be like 190, 195 in the K direction. So that's what you're after when you're trying to work these things. You're trying to get that unit vector along that. You want to get that unit vector along this, and then you can find the resultant force at point A. Is that making sense? The real trick comes in figuring these things out. Okay, so here we go. I'm going to switch over. I'm going to use ISO paper. I'm going to do this one first. So let's look at this right here. I've got this lovely cell phone tower, antenna tower. Use it for what you have. It's got 3 guy wires on it. It's got 3 guy wires on it. And we're ultimately going to have to figure out what the resultant force is. So I'm going to kind of walk us through this diagram here. So the tower itself is at the origin. I've got a force that's going to go along this one from D to C. I've got a force that's going to go from D to A, and I have a force that's going to go from D to B. And this X and this Y are going to be given to us in the problem. And I'll give it to you here in just a second. They're going to be given to us in the problem. This one's given us 4, this one's given us 6, this is given us 18. So I want to do this to show you how to use the ISO paper. So first thing, sometimes it really does help to give yourself different colors. So I'm going to give myself different colors here. So here's going to be my tower that I'm working with. So there's my tower on my paper. And that's going to be in the Z-axis. So now I can put in my line here. And this is going to be the minus x-axis, and this is the positive x-axis. Let me scroll out a little bit. And then I've got my ISO paper, so my ISO paper is really gonna help me out. This is my positive y, and this is my negative y. So this one is gonna be my point C. That was given here, so that's my point C. And now I'm gonna sketch in my vector. So there's my vector, and I'm told this is in the negative, it's gonna come down this way. So when I end up writing my vector, do this one, there we go. We're told that this is 24 meters. This will give me my other dimensions. This is 18 meters, and this is 16 meters. We know when I ultimately write this, I'm going to have a negative k, I'm going to have a negative j, but I'm going to have a positive I. So it's really helpful to go in and look at where you're going to end up. Because this vector is going to be pointing down, so it's going to be in the negative z. It's going in the negative direction in the y, so it's going to be negative there, but it's in the positive direction of the x. So I've got which way it's going to go.
So our origin is at the top of that tower?
No, the origin's right here.
And when you change 0?
Look at the direction of my force.
Okay, the other direction.
Yeah, the direction of my force. It's going from the top of the tower down. My origin's right here.
Gotcha.
So we've got, and because of what we've been doing homework-wise, well, this makes it easy. So we know that the magnitude of r, whatever r vector is going to be, right? We know the magnitude is going to be the square root of 16 squared plus 18 squared plus 24 squared. Plug that into the calculator. That gives me, just so keep us all straight, this gives me 1156, and that gives me 34. So now when I want to write r, my x direction is 16, the magnitude is 34, so that's the number that I'm going to put in front of my I. And the j, the magnitude is 18 divided by 34, and my k, it's 24 divided by 34. So that gives me my r vector along this, and if that's 600 newtons, my vector f is going to look like 600 times that r, and this could be, and if you're doing this, this was given as d, so this is RCD. So you'll see it a lot of times, like this will be my unit vector RCD will go along that right there. Now, if you want the gory, horrible gory details of what this looks like, you know, in the most general form, you get F is equal to F times my unit vector. And the unit vector in its most gory form is going to be XB, your final position minus your initial position, in the I direction, plus your YB minus YA in the J direction, plus ZB minus ZA in the K direction, divided by the square root of xb minus axa squared plus yb minus ya squared plus zb minus za squared. And if you start looking in that section of the book, this is kind of what they start out with. But I find it more helpful to start with some problems to look at it before you write the gory detail out. Because that looks awful, right? That looks awful. This looks a whole lot better. It's easier to see. So let's do a different one using the same system. Okay, so this time over here, this is going to be point A. So we draw our vector in. And we're told in the problem, even though we haven't done it yet, we're told in the problem that this is 20 meters. And this one is that one's 15 meters. Again, none of this is to scale. But now I can figure out the magnitude of that one pretty quick. The magnitude of RAD, and again, we're told this is going in this direction. That's going to be, we're told that was 20, so that's 20 squared plus 15 squared plus 24 squared gives me the square root of 12,001, which gives me 34.66 meters. Now if I'm writing out my vector, this is my unit vector, so I can call it a unit vector AD. We're in the positive x, we're in the positive y, but we're in the negative z. So this is going to be, on my positive x, it's going to be 20 divided by 34.66 in the I. This is 15 divided by 34.66 in the j. And it's 24, but it's got to be negative, so I got to put my negative in there, 34.66K. And that gives me my unit vector in that direction. And if we want to practice again, this time we'll put it here. We're also told this is going this way. And this is, we're told that that's 6 meters. We're told that this is 4 meters over here. So we can do the square root thing. So this is the magnitude of RD, we'll call this B, RDB. It's going to be the square root of my x direction, it's 4 squared plus, or it's 4 squared, 6 squared plus 24 squared. Gives me the square root of 628, which is going to give me 25.06 meters. My unit vector dB is going to be, it's in the negative x direction, so it's negative 6 divided by my 25.06. It's in the positive y direction, so that's 4 divided by my 25.06. And it's in the negative z direction, so it's a negative 24 divided by 25.06. So it gives you an opportunity to see how to use the ISO paper. gives you an opportunity to see how it helps. And you see how I get the unit vectors. Everybody doing good so far?
Would this problem be possible by adding all of the forces in the direction 0? Like the calculus example you showed us, would it be possible that way?
Probably not.
Yeah. That's what I was thinking.
No, this one, if, right now I've only used the problem to just do the unit vectors. But now if I want to do the sum of these vectors to find the resulting force on the tower, which we hope, right? Which we hope, if it's a radio antenna tower, we hope that we're balancing whatever force by the tower itself. And we really hope that the resultant force is only in the z direction. Otherwise, it's going to topple.
That's not good, right?
No, that's not good. No. Because if we're in statics, we want to be in equilibrium. So if I want to be in equilibrium, I need the resultant force, we hope, is going to be straight down on the tower, and we're balancing out the force from the tower at the top. Here's another diagram of how these things work, and the darker one made it a little tougher. Because we're given, okay, from the place on the boat where we're going to tie to, it's at the origin. And things are going to be in the negative z direction again, because we're going to actually use these 2 points as our tie points. And we know that this part is 50 feet away, and we know we're 30 feet from the plane that's created by the top. And if we put this along that side, we're telling us we're 10 feet to this point, and we're 40 feet to this point. So now it just becomes a way of how do I get to where things are, right? So you can look at it from this perspective. So let's go ahead and use my little handy dandy paper here. So this is going to be my x-axis. I only really need the positive direction in the y. And then I've got my z, because I'm going to go down. So if this one is 50 feet out, so I'm going to do 1, 2, 3, 4, 5. Give myself a little bit to play with. And then we're told that this is 10. And we got 1, 2, 3, 4. That's 5 right there. So there's my other part. This time I am actually drawing it to scale, and we're told we're going to go down 30. So there's 1, 2, 3. So we're going to do 1 at this point, and we're down 30. And that's at 10. Over here, we're down 30. So there's my first vector. You know that's 30. You know that this is 50. Actually, it may need to have come down here a little bit, but that's 50. So we got our 30, 50, and we know that this part is 10. So it gives you a way to really look at where my vector is. And then you proceed to follow it the exact same way. We can count the magnitude, or calculate the magnitude of that, which is easy now, because this is 10. So the magnitude is going to be, or this is going to be, the magnitude is going to be 50 squared plus 10 squared plus 30 squared for that vector. It's going to be the square root of 3,500. Which is like 59.2. And that was given to us in feet, so 59.2 feet squared. So that length of that is going to be 59.2 feet squared. But if I'm trying to just get the unit vector, I can go ahead and divide by, or go ahead and put them in my I, J, and K. I'm going to be in a positive X and a positive Y, but a negative Z. If we're told that the force is going in this direction.
Wouldn't it always go in the negative Z?
No, because if I'm asking what's the force on this bolt, that's one thing. But if I'm asking what's the force on this pylon, that would be going in the positive direction. Equal but opposite.
Yeah, okay.
So it's how I'm asking the question. Where am I looking for the forces? And as you start working some of these problems, guys, that's what's going to be one of the things. Is are you looking at it from the, you know, you can go all through all of this, get everything correctly, and your force is backwards. You know, that's one of those things when you're working the problems, that's where we're at. Okay, we'll do a couple more of these on Wednesday. You guys get to do them on Friday. Test on Monday.